Hello students, today we're going to be taking a look at section 5.6, the quadratic formula and the discriminant. So as you hopefully recall from Algebra 1, the quadratic formula can be used to solve any quadratic equation once it is written in the form ax squared plus bx plus c equals 0. Um, a lot of the functions or quadratic equations in the form of functions that we've been looking at, we've been doing a variety of things. We've been graphing. We've also been solving, but as far as solving goes, the quadratic equations may or may not have been factorable. So we have already used things like, or a technique such as completing the square, which works all the time. Factoring doesn't. A quadratic formula like completing the square also works all the time. So here it is. The solutions of ax squared plus bx plus c equals 0 with a not equal to 0 are given by the following. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. The equation is pretty self-explanatory. Once you assess what a, b, and c are in the appropriate quadratic equation, and of course also set equal to 0. It's pretty seamless. So solve x squared minus 5x equals 14 by using the quadratic formula. Well, like I said, you do have to set it equal to 0. So the first step, simply subtract 14. So what? X squared minus 5x minus 14 equals 0. A is 1, which they also note down below. B is negative 5, and C is negative 14. So negative b plus or minus square root b squared minus 4ac all over 2a. Yet again, in this case, though, be careful. Negative b, in this case, negative of a negative 5, which ends up being a positive, plus or minus the square root of negative 5 quantity squared minus 4 times 1 times negative 14. Now, I do recommend that you also put your a, b, and c values in parentheses accordingly. So specifically, when it's a negative value, uh, and also well, specifically, let's say the b squared value, if you don't put it in parentheses, that could end up being a mistake. So make sure you do that. And really, I just recommend all a, b, and c values, wherever they happen to be in the formula, put in parentheses. As you can see, that's all over 2 times 1. The radicand, we say, which is also defined as or referred to as something called the discriminant, negative 5 quantity squared minus 4 times 1 times negative 14. That quantity ends up being a nice perfect square. The fact that it is a perfect square will lend itself nicely to the next steps unfolding, but it's not always the case, as we'll discuss yet again, as we saw it actually in other sections. Anyways, negative b, negative of a negative 5 becomes positive 5 plus or minus square root. Again, the square root of 81 ends up being a nice perfect square. Because it's a perfect square, excuse me, it is a result that we know as 9. Um, so 5 plus or minus 9 all over 2. 5 plus 9 over 2, that's simply what? 14 halves or 7. 5 minus 9 over 2, simply negative 4 over 2, negative 2. Final answer is 7 and negative 2, which actually speaks to something we're very familiar with already when we looked at functions for the first time of this nature. They will, or this will, excuse me, cross the x-axis at negative 2 and at 7. It's a parabola that opens up with those two x-intercepts or roots. So as you can see here, I've completed some questions prior to doing this particular screencast again. I'm going to go ahead and reference numbers 1 and 13 as well as 15. I might skip number 3, but let's take a look and see what the nature is behind at least number 1 to start with. I'm going to scroll down a little bit. I have select problems that I have saved over the years, problems 1 and 3 in particular. Let's take a look. So number 1, as you can see, we have a quadratic equation. Again, it's x squared plus 2x. Let's see if I can move this. X squared plus 2x minus 35 equals 0. We're going to go ahead and actually, off to the right, kind of kind of forecast, I guess you could say, or predict really what the answers will be, because this is an actual factorable quadratic. X plus 7 and x minus 5 are the factors. X plus 7 times x minus 5 is in fact x squared plus 2x minus 35. But again, because it's equal to 0, we can solve by setting then x plus 7 equal to 0 to get negative 7 as one solution. And the other, of course, x minus 5 equals 0. Solve that, and you end up with x equals 5. Now, this particular section is not just kind of seeing if, in fact, you can solve the problem by any means necessary. It's by quadratic formula. So let's solve by looking at the quadratic formula approach as well. Now, we already know the answers are negative 7 and 5, and those are the answers by, in my opinion, the best approach, factoring. But again, we're trying to use factoring to kind of practice really with any type of quadratic, even though those that are not factorable. So negative b, so negative 2 plus or minus the square root of b squared, so 2 squared minus 4 times a, which is 1, times c, which is negative 35, all over 2 times a, which is 1. The radicand ends up being, again, a nice perfect square. If you do that math, and notice all my parentheses again, you'll end up with a perfect square of 144, the square root of which we should hopefully know simply to be 12. So negative 2 plus or minus 12 all over 2. Negative 2 plus 12 over 2, that's one solution, which ends up being 10 halves or 5. And then negative 2 minus 12 over 2, which ends up being negative 14 halves or negative 7. Predictably, again, we got these two solutions, based on the factors also from what we saw earlier, the solutions as such. Again, that being the easier approach in blue. But in red, we do need to prepare ourselves for that possibility. And again, the directions told us to use the quadratic formula anyways. Number 3 is similar, so I'll kind of just briefly touch base on that. I did do the factoring off to the right, and as you can see, the quadratic formula yields the same two results. So take a look at that on your own. Just try to reflect upon again how that could easily relate to number 1, and if in fact the directions didn't say you had to use the quadratic formula, the obvious choice in my opinion is factoring. Let me bounce back. I do want to make sure that we discuss, like I said, numbers 13, but also 15. These two respective problems and their answers, as you can see, are not very nice. Number 13 will have an irrational pair of roots, while number 15 will have imaginary roots as answers. We've already prepared ourselves in section 5.4 for imaginary roots, but this is going to dig a little bit more deeply into that idea. So number 13, quadratic formula. A is 1, that's the coefficient in front of x squared again. B is 6, C is negative 23. So if we plug in A, B, and C accordingly into the quadratic formula, negative B plus or minus again, square root of B squared minus 4AC all over 2A. The radicand ends up being 128. It is something you can break down where you do have, of the factors that remain, 8, 8, and 2. Technically, you can break 8 and 8 down, but why not stop there? Because technically, you could stop there or keep going. But why not just say, well, we have a perfect square. The square root of 64, of course, is just 8. We're left with then 2 under the radical. So the radicand of just 2. Don't forget, you can actually also split this up. This is something that is always plausible when your denominator is a single monomial term. So negative 6 halves plus or minus, like I said, 8, then root 2 all over 2. So again, I split the problem into two separate fractions, which is, I think, more conducive to simplifying than in the last step, as you can see. Not surprisingly, negative 6 halves, which is negative 3. 8 halves reduces, of course, to 4, so that is a good final answer for number 13. Negative 3 plus or minus 4 root 2. And again, these are two irrational roots. It is, in fact, a parabola that crosses the x-axis at those two irrational values. The decimal approximation for those we will later maybe dig in more deeply on. Number 15. Again, we're going to go ahead and solve this particular quadratic by the quadratic formula. Off to the right there, I've noted A is 1, B is negative 6, and C is 21. So there it is. Plug in all your appropriate values for A, B, and C. I did it again in parentheses. And then what happens here, as you can see here in this step, negative 48 that radicand value, because it's negative, we won't have real solutions. I still broke it up accordingly, 16, 3, and -1, 16 being a perfect square, the square root of which, of course, is 4. So that particular root ends up being 4 root 3i. I again split it up into two different fractions, so 6 over 2 plus or minus 4 root 3 over 2, and then of course still there I. 6 halves is 3, 4 halves is 2, so the two final answers, even though this parabola doesn't cross the x-axis, we have, and talked about this in the past, we have two imaginary roots that will help us in different ways. We haven't really talked about exactly how the graph may play out with these two roots in mind, considering it doesn't cross the x-axis. But it will later most certainly help us to kind of frame, if we knew these in advance, what the quadratic would actually look like. We haven't talked about it quite yet, but that's where we're headed. Final two answers, 3 plus or minus 2 root 3i. Those are the imaginary roots of this particular quadratic. Again, it doesn't cross the x-axis, but it is noteworthy. Okay, let's move on to the next page, page 37. So I've already discussed the key term from what's the resulting quantity under the radical. We also call it the radicand. But more specifically, in the context of what we're going to be talking about here now is, as you can see, the discriminant idea. The discriminant, the expression under the radical sign, so the b squared minus 4ac quantity in the quadratic formula is called just that. So there's four different aspects that we need to dig deep into here. The first of which is the following. If the discriminant is greater than 0 and it's a perfect square, then you're going to have two rational roots. Now that is the most, I could say, efficient kind of outcome as far as deciphering what kind of graph you're going to take a look at, I guess you could say, but also how it relates back to if you did have a choice to maybe pick between factoring versus, quadratic formula, let's say, I would argue that if this result plays out where your discriminant is in fact a perfect square, then factoring is your best option. If in fact I gave you the choice between the two. Certainly factoring, and then you'll get two rational roots. Two rational roots meaning just two values that are numbers you can write as fractions. Irrational, of course, meaning two numbers that you cannot write as fractions. So like a square root answer, for example, that you can't simplify. The next piece to this is when b squared minus 4ac is also greater than 0, but it's not a perfect square. This would then lend itself to two irrational roots. So again, you're going to have two roots that you can see on the graph. Unfortunately, you cannot write those two answers as fractions, therefore they're irrational, and also you cannot factor those types of questions. The first, again, is the best as far as the ease of solving and all the options at your disposal. The second is not as easy, but it's certainly better in most cases than the last two. As you can see, b squared minus 4ac, when it's equal to 0, there will only be one rational root. I'll speak more about that later, but more specifically, if this is the case, the rational root, even though it'll be 1 point of which the parabola crosses the x-axis, we're going to define it more specifically as a repeated rational root. So it'd be like, for example, if a parabola crossed the x-axis at -2, your function would actually start off as x plus 2 times x plus 2, or x plus 2 quantity squared. The last thing to finish with here is the discriminant of b squared minus 4ac being less than 0. And if this is the case, you're just simply going to have two complex roots. Because I don't have a whole lot of time to completely do every single example or problem here on this page, I'm going to just finalize things by going back to the prior page on page 36. When I had done number 13, I had actually gotten a non-perfect square radicand or discriminant, so we knew that the two roots were going to be irrational. Well, on number 15, when I got -48, I knew in advance that my two answers were going to be complex. So that's just, again, kind of keep in mind how this discriminant concept kind of helps frame our understanding even before we solve the problem. All right, thank you.